So we have that quadratic equation that's going to be called standard form for the different things that we find. These letters that I've highlighted in these different colors, the red, the blue, and the green, they all tell me something different for this equation. So it's important that we start figuring out what those numbers tell us so that we can quickly find out attributes to this quadratic without really having to graph it in Desmos and do all of that. One of the things that quadratic equations have are a y-intercept. We talked about these last year. The y-intercept is where the graph crosses the y-axis. The way that we can immediately know this from the equation, meaning we don't have to graph it at all, is if we look at the very last number, that value c. If we look at what c is, that's going to be where my graph crosses the y-axis. So I don't have to do any work. If it asks me for the y-intercept, I just look for that last number, and that's where the graph crosses the y-axis. Does anyone remember what that vocabulary word parabola is? I see some hands doing this. Yeah, it's a U-shaped curve. So the quadratics make a shape called a parabola. They're no longer lines. They're called parabolas. So it's the U-shaped curve created by a quadratic. It's called a parabola. Does anyone remember what the vertex of a quadratic is? We talked about the vertex last time with transformations where we were moving it side to side or up and down. The vertex is the highest or the lowest point on that parabola. So highest or lowest point. Right, so it's either going to be the top of the hill or the bottom of the valley. That's my vertex. But the vertex has very specific letters for it as well. The letters are H and K. Now these will not look familiar to you right now because there's no H and K in this equation, right? We only have A, B's, and C's. However, do you remember us using H's and K's last time when we did transformations? The K numbers that we would add or subtract on the end moved the graph up and down because it's a Y value, up and down. And the H moved things side to side. That's the number we stuck inside the parentheses. So this changes the vertex, or this creates my vertex, the H and K that I choose to transform my graph. Now a maximum or a minimum value is simply the Y number or the Y value of the vertex. It can't have both a maximum and a minimum. It's either going to have a maximum or a minimum. If the graph looks like this, if this is the way the parabola goes, is that a maximum or a minimum? Maximum, because it has a large point or a tallest point. Maximum means big. And the parabola looks like this. What kind of value does it have, max or min? Minimum, because it has the smallest point, a valley. But both of those vertexes, which is the highest or the lowest point, create those maximums and minimums. Now the axis of symmetry, which we occasionally or all the time shorten to AOS because axis of symmetry is a lot of letters to write down, AOS. Does anyone remember what the AOS is? It's the line that's in the middle, absolutely. We're going to call it the dashed line, or the dashed invisible line that cuts the graph in half. So it's going to come down and chop the parabola right in the center or right in the vertex. Now the equation for this axis of symmetry, if we don't have it graphed, which we're going to try to avoid having to just graph them, is going to be x equal to whatever that h number is. The h number, oh, I used the wrong color. This should be h. So sorry. So x equal to means it's a Vux line or a vertical line that comes through the center of the graph through that vertex, which is why it's the same number as the purple h from the vertex. Okay, parabolas have a lot of vocabulary associated with them, which is what we're trying to remember today. One of the most important things you can learn about a parabola are the roots, zeros, x-intercepts, and solutions. In Algebra 1, we called those the rocks. Does that sound familiar for you? Yeah, these roots, zeros, x-intercepts, and solutions are just the locations where the graph crosses the x-axis. So that's my rocks words. The rocks words are found here where it only crosses one time. That means that parabola has one real solution. Or here where the parabola crosses the graph twice, bless you, it has two real solutions because it crosses the graph twice. But the parabola could like straight up miss the entire axis. You see how here it doesn't cross this axis at all? It's going to have no real solutions, which also means it does not have x-intercepts, it does not have roots, it does not have zeros. Those four vocabulary words are all the same. So if we look at a couple examples of what parabolas look like in large, we've got these two examples here. Is this parabola, the first one, a happy or a sad parabola? It's a sad parabola because it's going down. So we can tell all of the information about this axis of symmetry, about this parabola, even though it's a sad parabola. We'll start at the top here. We're going to start with the vertex. The coordinates of the vertex are what? Close. Well, so see here, this is where it lines up with that number and then with this number. So we have these two numbers, like you guys said, -1 and 1, which create my vertex. That also means I know a bunch of other information if I know my vertex. I know my maximum value because the maximum value is just the y value of that vertex. So how high did that parabola go? 1, so that's my maximum value. That's also the same number as the y value in my vertex, because that's how high it goes. I also know my axis of symmetry, because what number does my axis of symmetry cross on the x-axis? -1, which is, again, the same number we had in that vertex. So those two numbers for my vertex actually answer 3 questions. They answer the vertex, and they answer the maximum value and axis of symmetry. Now we can talk about the y-intercept because that's just a location on the graph. Where does this graph cross the y-axis? 0. So my y-intercept is just the coordinate point 0, 0, because that's right here where the graph crosses the y-axis. 0, 0, no, it's not infinity. 0, 0 is a location. It's talking about this location right here. Now, infinity does come into play when we talk about the domain. So we're going to also answer domain and range for all these parabolas. Domain is which letter, x's or y's? X's. So we're looking at the x values for the domain and the y value for the range. If we look at the x values, that means I want to look at the arrows on the left and the right. Are they ever stopping on the left or on the right? No. So how do we answer that question for domain? All real numbers. Another way we can answer this, just throwing it back to interval notation. Remember that interval notation would say that that goes from -infinity to infinity because it's going the entire number line on the left and the entire number line on the right. For the range, we're just trying to describe where the graph shows up from bottom to top. So does it ever stop on the bottom? No, it goes all the way down to -infinity. But does it stop on the top? Yeah, at 1. That same number that comes out of my vertex, it stops at 1. So my range in interval notation is from -infinity, because of the arrows, up to 1, because that's my vertex. In inequality notation, that's y less than or equal to 1. Now, why am I saying less than or equal to for this range instead of greater than or equal to? Because it's a sad parabola, so it's less than a certain number. Because this has as high as it goes, everything else is smaller. So I use the less than symbol that looks like my left hand because it's going down. It's less than. It's a sad parabola. What I want you to do is I want you to think about all the things we just talked about for this problem, and I want you to try the problem right next to it. I'm going to give you a few minutes, get as much of the questions answered as possible, and then we'll go over it together. For the second example here, I would have started again with the vertex, and I would have seen that the vertex is at the x value of 2 and at the y value of It's actually -1. Whoa, let's talk about why that's -1 versus 3. So remember, we're looking at the coordinate point just right here. That means it has an x value of 2 and a y value of -1. Oh, wow, it's not showing up on the screen. There it goes. 2, -1. So it goes over 2 and then down 1 to find that lowest point. And since I know that's the lowest point, what is the minimum value here? -1. Same number as my vertex. And since I know my vertex, I also know the axis of symmetry. It's going to be the first number, x equal to 2, because that's where that dashed line crosses the x-axis. Where was the y-intercept here? 3. So we would answer, technically it would be the coordinate 0, 3, but if you answer 3, that's still giving me the same spot on the graph. I would like for it to be a coordinate. And oh my gosh, we didn't answer the zeros on the first one, did we? My bad. Okay, so the zeros are the places where the graph crosses the x-axis. Let's look back at the first one. Where does this first one cross the x-axis? What two numbers? -2 and 0. That would be my zeros. The numbers -2 and 0. What are the zeros for the second example then? 1 and 3. Those are the locations where the parabola crosses the x-axis. So those are my zeros, or my rocks. Roots, zeros, x-intercept solutions. What's the domain of this graph? Does it ever stop on the left and the right? No, so what would we answer? All real numbers. That's going to be an automatic response for pretty much every graph we learn about this year, minus a few. In interval notation, that's -infinity to infinity, because it's the whole number line, from the smallest number we can think of to the largest number we can think of. And the range has everything to do with this minimum value. So definitely -1 is going to be in there. That's the bottom of the graph, though. So I start at -1. And does it ever stop on the top? No. So we go to infinity. And if we write that in inequality notation, I'll scoot this over so you can see it a little bit better. In inequality notation, that would be y, some symbol, and then that -1. What symbol goes there? Less than or greater than? Greater than or equal to, because this is a happy parabola that's all above 1, -1. Okay, so how do we feel about parabolas? Is some of this vocabulary coming back from last year when we talked about all of this stuff? We spent a long time in Algebra 1 talking about parabolas. So we're going to go through 2 more examples here just to make sure we've got all that vocabulary down. So if you open this up on the back page, we've got a couple more examples for us to do together. One of the things on here we have not seen before. So I'm going to do the first one with you, and then you will take care of the second one. We'll do a little I do, you do. Okay, this time it's not cute and doesn't have like all the little arrows, but we can still find all the things. What is the location of the vertex? This point right here is the vertex where it's the highest or the lowest. So I want a coordinate point. -1, -3. Because the places that it would cross if I was drawing lines straight up and straight sideways to the axis would be here at -1. And here at -3. Which means, what is this, a maximum or a minimum? Does it have a max or a min? A maximum. And what is that maximum value? That's as high as it goes. I know that's a small number, so it doesn't feel like it should be a maximum point, but that's as high as this parabola goes. I then also know the number for axis of symmetry. It's the same number from the vertex, x equal to -1. So let's draw in that axis of symmetry here just so we know what we're finding. We're finding a dashed, invisible vertical line that cuts through the parabola right in the center. It also crosses this number, -1. Now, you may not have been asked the words direction of opening before, but it's just as straightforward as it sounds. Which directions are the arrows going? Down or up? Down. So this is opening down. That's how we would answer that. It opens down because the arrows are going down. Pretty simple question, just may not have been asked that before. It gets pretty important in Algebra 2. The domain for this graph, we check the arrows on the side and the side. Do the arrows go off to infinities?
Yes.
Yes, so we're going to call this all real numbers. And the range, since this is a sad parabola, is going to deal with that number -3, but is it going to be less than or equal to or greater than or equal to? Less than, because it's a sad parabola. So all the numbers are smaller than or below -3. That's where the whole graph shows up. Now this next part, you have not ever been asked this before, so this is new. Increasing and decreasing intervals. What I'm asking for is if you were literally walking along this parabola, like walking with your legs, are you going uphill or downhill? So that right here, yeah, up here, are we going uphill or downhill? Up. That is called an increasing interval. When do I stop walking uphill? Well, what is this point called? Starts with a V. The vertex. I stop and I change direction at the vertex. And then all of a sudden what happens? I start walking down. So that's my decreasing interval. So if we were going to notate this so that you have some notes on your graph of what we're doing, we'd be walking uphill. All these little arrows going up. Then when we get to the vertex, it changes and we start going downhill. So to talk about the increasing and decreasing intervals for me, the way that we're going to do this is talking about which side of the vertex you're going up and which side of the vertex you're going down. So are we going up on the left side or on the right side of the vertex? Left. So we would say we're increasing on the left of the vertex, but we're just going to say the value -1. That's where we're going uphill, on the left of it. And which side of -1 are we going down? On the right side. That's where we're decreasing or going down. On the right side of -1. Do we see that? It's usually confusing for students because I don't get it. It's going up, it's going down. If you were walking along the graph, are you walking uphill? That's increasing. Are you walking downhill? That's decreasing. And all you have to tell me is left or right of this middle number, -1. Again, vertex, so important because it has all the answers basically. Okay, so we just did this example. I would like for you to try the next one. Work on it for a little bit, see what you can do, and then we'll check it. Okay, if you wanted to check your work, look up at the board. I got all my work up there. I even annotated my graph, which is really helpful to do, especially with the increasing and decreasing stuff, to draw the little arrows of whether you're going up or down, or color coding it red and green, down, red for down, green for up. I kind of like doing that. So we have a vertex here at 1, -4. Once we have the vertex, we have a lot of different answers. We have that this is a minimum value at -4, that's as low as it goes. We know that the range would be above that since this is a happy parabola. We know that the direction is up because the arrows go up. We know the axis of symmetry is that middle number, -1. And we can see that it's increasing or going up on the right side of that and going down on the left side of that. So we know how to answer increasing and decreasing intervals. Are there any questions about these types of attributes that we can talk about for a quadratic or for a parabola before I move to something else? Okay, just a couple more things about parabolas. We have a separate type of equation that's not written on our front side. The front side is called standard form. This is called vertex form. We actually used this last time to talk about transformations. So let's think back. The color coding is different, but what did this number in the very front do to my parabolas last class whenever we were transforming them? When we put a number in the very front, what did we do to it? Say again? Reflected it. If it's negative, that can be a reflection over the x-axis. What else could it do? If I made that a number like 5, what would that do to my parabola? Make it, I think I heard it, make it narrower. And if I made it a number like 1/5, like a fraction, it would make it wider, which is our vertical stretches and shrinks. Just by looking at a vertex form equation, like we did last class, we'd be able to tell or create a stretched or a shrunk graph. Does anyone remember what the h does that's in the center? When you added or subtracted a number inside those parentheses, what happened to your graph? Moved left or right. So yeah, we can move this graph horizontally, translate it to the left and to the right. And then we had some number that we added at the end. Does anyone remember what that did? Moves it up and down. Fabulous. Now that's what happens when we transform the graphs. We can make it flip over, stretch it, shrink it, move it side to side, move it up and down. But what's really interesting is that actually this formula tells me what's called vertex form. It tells me the vertex. The vertex, if you remember our color coding today, was h, k. Which means whatever number I have here in the center is going to be my x value of my vertex. And whatever number I have here at the very end is going to be my y value of my vertex. The a value doesn't really tell you anything about the vertex. It just tells you the shape of the graph. So without graphing these things, without looking at a parabola, I can find the h and the k. We're going to skip to the example 2 or example 4 first, actually. What number is inside those parentheses? Looking at example 4, skip number 3 for right now. 3. Now, since it's in parentheses, high O tells me horizontal is inside and opposite. So I'm not going to write down positive 3 for my h. I'm going to write down the opposite. What's the opposite of positive 3? Negative 3. So my h value is negative 3. And my k value is exactly what I see, not the opposite. That means the k value is negative 1. That would be the vertex if this was a whole coordinate point for this parabola. I didn't have to graph it or anything, and I already know the vertex. So I can know a lot of information about what the shape looks like. Now if we hop back up to number 3, I skipped it on purpose because what number is missing, h or k? K, which means what is it? Since it's not there, 0. But then we have our h value here. It says negative 2, but what number do I actually write down? Positive 2. So 2, 0 would be my vertex, h, k. So for number 5, what's the h value? Negative 2. And what's the k value? 4. The opposite of the inside one, exactly what you see on the outside. In number 6, what's the h value? And what's the y value? Or k value, sorry. So we have these x and y coordinates for my vertex, h, k. That's the letters that we assign them for the vertex, h, k. So now we don't have to do a lot of work. We just look at the graph or look at the equation and we say, aha, that's the vertex. I don't have to go to Desmos. I don't have to graph anything. I just know that's what it is. Okay. Jumping around, just using some more things about a parabola. We have these vertexes here and half of a parabola. If I asked you to finish graphing the parabola, to finish plotting the points, and I gave you this information, I actually gave you everything you need to know to by hand graph the rest of it. Since the axis of symmetry cuts it in the middle, shouldn't all of those points just simply be reflected on the other side? So what I'm going to do on this first one is I'm going to physically count how many dots, how many lines are in between the dot and the axis of symmetry. How many lines, are in between this first coordinate and the axis of symmetry? How many jumps did I have to do? 1. So how many jumps should I go away for it to graph the next one? Just the same number, actually. I'm reflecting the point. So if I go 1, then I'm going to go 1. For this one, the second point, how much did I have to jump to get from that point to the axis of symmetry? 2. So how many do you jump away from it again? 2. So that's where my next point's going to be. On the same y, the same line, the same height, just scooted over that many times. How many jumps did I have to do to get from that third one to the axis of symmetry? 3. So how many am I going to jump away from the axis of symmetry? 3. 1, 2, 3. We've just reflected those points, and I can finish making a really nice looking parabola. So So if you reflect the points of the next one, we should have a coordinate point here at -3, 4. The next coordinate point should be at -2, 1. And the next coordinate point should be at -1, -4, where we just reflected those points. Very cool. All right, for real life parabolas, like I said, it's generally easier to see these on Desmos than on the calculator, simply because the Desmos zoom feature is a lot easier to use than the graphing calculator zoom feature. They work the exact same, but it's just easier to use on Desmos. So this problem says the parabola shows the path of your first golf shot, except mine would not go that far. I'm terrible at golf. Where x is the horizontal distance in yards and y is the corresponding height in yards. The path of your second shot can be modeled by this function, f of x equal to 0.02x times x minus 80. Fabulous. On your Desmos screen that you have already pulled up on your computer, I want you to graph this function, because I want you to see what that looks like. So we're going to type it in exactly as we see it. F of x equal to 0.02x times x minus 80. So if we're comparing these two golf shots, the first question says, which shot travels farther before hitting the ground? So let's just read these graphs for a second. Shot number 1, which is the shot in the picture, how far does that golf ball travel before it hits the ground? If you're looking at that trajectory, when does it hit the ground? 100. So the first shot travels 100 yards because we see that it literally hit the ground at 100 yards. The trajectory for the second is the one that you have on your Desmos. When does that one hit the ground? So it hits the ground at 80 yards. We are looking for these two numbers at what are called the roots, zeros, solutions, or x-intercepts. So really this question, if it was just a math question, would have said, which solution is more? But because it's a real-life problem, it's asking which shot travels farther. So which shot travels farther, shot 1 or shot 2? Shot number 1. Okay, part B says which travels higher. Okay, let's read these graphs. For that first shot, the one that's printed on your paper, how high does it go? 25. Remember, this is the side to side. This is the up and down number. Your vertex has both side to side and up and down. So how high does it go? 25 yards. And shot 2, the one that's on your Desmos, how high does that one go? 32. That's how high the vertex is. That's the maximum value of this parabola. So which one travels higher? Shot number 2. Okay, so occasionally we're going to be comparing parabolas to each other, and this vocabulary is very easy to compare, especially when it's in real life. You're looking at it like it's an actual golf ball getting shot off and landing back on the ground. Okay, if we do the next example, we don't have a picture for this one, so that means we're going to have to graph it ourselves. But the question says, a softball player hits a ball whose path is modeled by the function f of x equal to, whoa, that's a crazy big decimal, x squared plus another crazy big decimal, x plus 3. I don't want to graph that by hand, but because we're going to be asked the highest point, we're going to want to see it on a graph. So let's go to Desmos. We're going to change this equation that's in our Desmos to the equation that's on our paper, so I'll give you a second to type that in. When you have that typed in, it's obviously going to be really kind of far away, so you'll have to zoom out and scroll to make sure that you see the graph correctly. But once we see it, we can answer the questions for Part A and Part B. Part A says, what is the highest point this ball will reach? What vocabulary word that we learned today are we going to look for the question, what is the highest point? The maximum value, absolutely. So I look at the highest that it goes, and how high does this go? 25, and we're going to leave it with 1 decimal, 25.6 feet in the air. Cool. That's its vertex, or that's its maximum value of the vertex. Part B is a very interesting question because it's actually going to require us to do a little bit more with this particular parabola. It says, if the ball was hit to center field, which has an 8-foot fence located 410 feet from home plate, was this a home run? Okay, for something to be a home run, if you don't understand sports, that means it has to go over the wall, which means at the distance of 410, for it to be a home run, our trajectory of this ball needs to be above 8 feet. Okay, I can't really tell what's happening here on this parabola because it's so far away. So what I'm going to do is I'm actually going to plot the coordinate point for the back wall. The coordinate point is 410 feet away and 8 feet high. And just to be funny, I'm going to write the word wall here. So there's the wall. It is 410 feet away, side to side, and 8 feet tall, which is why I made that the y value. Now, if I look at our trajectory here, is that a home run? Look up at my screen. Even if you don't have it graphed yet, look up at my screen. Did our ball go over the wall? Is the trajectory above the wall? Or isn't the wall above the trajectory? Yeah, so if this was legitimately a wall, would our ball go over the wall? No. So we were able to answer this question using only math without having to get out there and actually try to hit a home run, which would be nearly impossible for me. We would say no, because the wall is higher. Than the value f of 410. So where the wall is higher than what our parabola is 410 feet away. Because when you look back at these notes, you're going to be like, how did I figure this out? I want us to do a little sketch here of what happened. So we had this parabola, okay, and we said that its vertex, or its highest value here, was 212.7 comma 25.6. But that's where we got this highest value here for the first question. How high does it go? The next thing we did was look at the wall that would be here, and we saw that the wall was at 410 comma 8 feet, and that it was larger than the trajectory of our ball, so that it would hit the wall, not go over the wall. The real world problems are a little bit more difficult because they don't just ask you what's the vertex or what's the maximum. They want you to know what these parabolas look like in real life to be able to know which of these vocabulary words that we've discussed all day that it's actually talking about.